So how do we solve the steady state heat conduction equation, or what we have achieved in the previous video? The final equation was very close to a very single term, but let's go into the most complex possibility first. So I'll give you a general idea of what all things will be included in this. So we are going to understand solving heat diffusion equation. So our final heat diffusion equation in Cartesian coordinates was something like this. Without any assumptions or without any simplifications, the core equation which we have derived is like this: del by del x into k del t by del x plus del by del y into k del t by del y plus del by del z into k del t by del z plus q dot gen is equal to rho Cp del T by del T. So now let's understand the things which this equation says to us, which is helpful for solving the problem or solving this equation. So first thing, we can make a note of this. These are second order equations. This is a second order equation, differential equation, and more importantly partial differential equation. Okay, and the second order is with respect to, or I can say WRT, with respect to spatial coordinates. That is important. With XYZ it is second order. We can see this by from here. This term, if the K was constant, or even if this is not constant, the temperature has a second order differential with X, has a second order differential with Y, has a second order differential with Z. Now the second thing is, it is first order partial differential equation with time. This is visible from this term which says the energy stored changing with time. So del T by del T is the first order term. It's the first order partial differential with time. Now we'll use this two information to understand the things. And this heat generation term is very simple. It's not having much complexities until and unless heat generation is given in a form of some equation. If this value is a constant value, that meaning 2000 kilowatts, that heat generation value, a constant heat generation value, is not tough to understand. Okay, so these two combined gives you some information that it is a boundary value problem, and second, it is also an initial value problem. So this is a boundary value problem and an initial value problem. Okay, boundary value problem comes as we have spatial coordinates, and this comes, initial value problem comes because we have time involvement. So both these things will be included. For this to solve, for this condition to satisfy, will require the information which is will need two conditions, and for this we'll need only one condition. Why so? It is because with space it is second order differential equation, hence we'll require two conditions. With time it is only first order differential equation, that's why we'll only require one condition. Okay, so that's all for different boundary conditions. There are multiple possible cases. So for initial condition there is only one case or only one possibility, that at some time t0 or t0 my temperature x at any location x, y, z and t0 is given as some value of t0. So this completes my initial value condition. This is the one condition which is required, can be satisfied using this one given data. What is the data? That data is at some specific time my temperature value is known at at a location, at xyz location. Okay, now there are multiple cases possible for boundary value conditions. So that boundary value condition or boundary condition can have multiple possibilities. So we'll go into that conditions in the next video. Okay, thank you.